I wrote the same AI project with Python and Rust. After comparing Python and Go in my previous video, I listened to your comments and now I'll write it in Rust. Let's see if this bad boy can outperform Python in speed and scalability. After all, nothing compares to the thrill of writing the same code for the third time. But I get why you guys suggested Rust. Rust is gaining popularity because of its efficiency and speed. Plus, it's getting new tools for data science like Polars. This project is a recommendation engine that builds a discovery screen that adapts to a user's interests and optimizes revenue. As a data scientist, I of course built it with Python and chose to deploy it in the easiest way possible, which was to run and save recommendations for all users every 12 hours. After seeing a revenue boost from recommendations, we decided to make it real-time for a better user experience. This involves two main parts. Firstly, we update the recommendations almost instantly whenever a user interacts with an item. When a user does something, like clicking an item, the data is sent to our recommendation engine through a tool called Kinesis. The engine then updates or creates the user's recommendations and saves it to S3, which is just a cloud storage service where you can save and download files on the cloud. The second part is an API that uses the saved recommendation files and other data sources to create personalized discovery screens for users. We only need to improve the second part because it struggles with high amounts of traffic. The API was mainly written in Pandas and NumPy, two highly efficient libraries written in C. Only the last function had to be written with Python operations to deduplicate, promote, and rearrange items. Although I tried to optimize it as much as possible, it took more than 60% of the processing time. But the overall processing time was still less than 70 milliseconds, which was good enough to try it out. The problem came when we started rolling out to 5% of users. The response time skyrocketed to 5 seconds. To fix it, we had to make 46 copies or pods of our system working in parallel to just handle the small percentage of users. If we were to make enough pods for 100% of users, it would be way too expensive and wouldn't even fit within the maximum limit of pods. If you're wondering why Python scalability sucks so bad, I will cover it later in the video, so make sure to stick around. We now need another approach to deploy this project. We started with Golang and even made a video about it. Then people suggested we try Rust and Polars. Polars is a data frame library that claims to be faster than Pandas. I wanted to start with it and see whether Polars will live up to its hype. After learning about Polars, I discovered it's faster than Pandas because it can use multiple threads and CPU cores, while Pandas can only use one thread. This makes Polars great for tasks like running data wrangling on a notebook or scheduled tasks, but it's trickier for real-time APIs like ours, where many requests come in at once. This could mean that some requests will get a lot of resources while others get very few, especially if you're limited in resources, resulting in non-consistent response times. Still, I wanted to see what the hype was all about, so I tried it out. I started by comparing performance of Polars and Pandas using examples from tutorials and documentation. The dataset used here is dummy data generated by NumPy's random function with 10 million rows. Initially, Polars, which uses Rust under the hood, was much faster. But could Pandas catch up if it uses more resources? I tried using a library called Swifter to make Pandas run on multiple threads and CPU cores, but it still was slower than Polars. Next, I tried a more real-world example using the Iris dataset from Kaggle, which is only 150 rows. Surprisingly, Polars was slower than Pandas. However, when I increased the dataset by duplicating the rows 10,000 times, Polars came out on top again. This shows that Polars is great for handling large amounts of data, but for our deployment use case, we don't usually deal with big datasets here, so Pandas might be faster. Even though Polars wasn't looking too promising at first, I tried to learn Rust anyway and give it a try. I started by creating a simple function in Python and Rust that sums up the first n numbers, just to get a taste of the performance difference between the two. Rust was a whopping 50 times faster. This speed enhancement is usually lower when it comes to production code, but it's a promising start. Now let's start implementing the recommender engine. We have 4 parts to implement. The first is to use the recommender objects and the NumPy alternative to generate a personalized user interscore for each item. The second step is to prepare the shells by joining the output of step 1 with 3 different data frames, then grouping and aggregating them. The third step is to convert the data frame into a list of objects or containers that make it easy for accessing and modifying elements, which is essential for the next step. The fourth and final step is to build the whole discovery screen by looping over the objects above to arrange shells, deduplicate elements, and rearrange items. In the first part, I used our Rust math library to sample the multi-arm bandit recommender engine. Those operations were 20 times faster than Python's. In the second step, I used Polars to replicate the Pandas code that joins, groups, and aggregates data. Polars had all the functions that I used in Pandas. I would say that the library is pretty comprehensive. It had 2 types of execution, eager and lazy, which caused some confusion at the beginning where I kept switching between the two, which slowed down the processing time quite a bit. It took some time to figure out how to optimize Polars, but once I did, it was easy to work with. Even after all these optimizations, Polars was still 1.8 times slower than Pandas. But it was just 16 milliseconds slower, so I kept going with the rest of the code, hoping that it would be faster than Python overall. In the third step, Rust was impressively faster than Python, where it was able to convert the data frame into a list of structs 6 times faster than Python. As for the fourth and final step, there was a lot of complex code involved in building the discovery screen. Luckily, ChatGPT was able to generate most of the code without many errors, thanks to the well-structured functions I was working with. Despite its complexity, breaking down the code into specific functions made it easier for ChatGPT to handle. In the end, this part was 3.5 times faster than Python's implementation. Overall, Rust was 40% faster than Python. While this is a significant improvement in response times, it might not justify switching to a whole new programming language. The part that slowed things down the most was using Polars, so I decided to take a similar approach to when I switched to Golang, ditch the data frame library, and use maps, structs, and regular loops to join, group, and aggregate data. In Golang, the data frame library was over 10 times slower than Pandas, so it was too slow to even be a usable option. However, Polars performed pretty well in comparison, but let's see how much we can squeeze out of Rust by removing Polars. After writing the code that replaces Polars operations, the code was 4.9 times faster than Pandas. That resulted in Rust being 5 times faster than Python in the overall execution time. Now that's a significant improvement in response times. So the question now is, how will Rust handle large amounts of concurrent requests compared to Python? I tested both by implementing an API for both languages. The API reads data from memory rather than a database to focus only on processing time. I started by testing just one concurrent request. Both Python and Rust had very similar response times to the ones I showed before. But as I increased the number of concurrent requests to 10, Python's response time shot up 10 times, reaching more than 600 milliseconds, which is too slow for production. However, Rust's response time with 10 concurrent requests was only a bit slower, still under 20 milliseconds. Scaling up to 70 concurrent requests, Python's response time went over 4 seconds, while Rust stayed under 100 milliseconds. Now that is impressive. So why the big difference? It comes down to how Rust handles requests in complete parallelism, where multiple requests are executed simultaneously at the same time. But Fast API operates asynchronously. Unlike complete parallelism, asynchronous execution only handles one request at any one time, but can switch tasks when waiting for a non-blocking operation to finish, like fetching data from a database. Instead of waiting for the data to come from the server, it works on the next request to not waste any time. This might be good enough for some backend applications where most of the response time is spent getting data from databases. But in data science projects, you can expect to have more functions with heavy processing that will execute one after the other and not asynchronously. I hope you learned something from this experience. Thanks for watching and have a wonderful day.